In this video, I will explain what is response spectrum and elastic design spectrum. Elastic design spectrum is the special case of response spectrum or spectra, which is used in the dynamic analysis or the earthquake analysis of structures. So it's important to understand what they are to be able to use them correctly, even when you are making hand calculations or when you are using a software. First of all, earthquake load is not a load that acts on structure directly. The soil under the structure or beneath the structure moves because of earthquake depending on time. So you see here, earthquake is not a force. It's the movement of the ground or the earth or the soil to which the structure is attached by means of fixed support generally. It's not like wind force or anything like that. Thus, during earthquake, soil under the structure has a velocity and acceleration. To illustrate this event, the single degree freedom structure given in this figure is used. Now you see here the structure has an internal damper and columns which provides elastic stiffness to the structure, and mass is lumped at the midpoint of the floor. As you see here, the structure's columns, legs of the body is the structure here, moves with the amount of Ug. Ug is the ground displacement which is induced by earthquake. And then because of that the legs moved in the amount of Ug, or yes, and this displacement has also an acceleration. If you derivate Ug with respect to time 2 times, you will obtain the acceleration induced by earthquake. So earthquake acceleration is this much. And in this direction, in this sense. Okay? And in the superstructure, an additional, you see, first assume that the structure makes a rigid movement. With the earthquake. And this amount, or this amount, is Ug. And because of F equals ma, Newton's law, this effect creates a force, a non-visible force, as if to the structure an F acts. Because of this F, the structure still attached to the ground, but the ground displacement do not occur anymore. But the upper part of the structure makes a movement. This is U. And how this occurs in a normal structure? Without thinking the free vibration, forced vibration, a force acts to the structure. We have M here, and it makes this U. Okay? And the total displacement of the mass is U times Ug, total displacement of the mass, which is lumped at the center of the flow. Okay. So as a result, we get this shape, which is the combination of earthquake movement and its effect, as if an F force acts to the structure. Here A is the acceleration acting on the M mass. The internal forces developed in the structure are column elastic forces, column stiffnesses. If we actually, this is wrong here. This should be K divided by 2, K divided by 2. There is a mistake here. Okay, so Ku divided by 2, Ku divided by 2 we shall obtain. K is the total stiffness of both of the two columns. This should be K divided by 2, K divided by 2. So acceleration is in this sense. Forces are in this sense. F equals ma. So we see A is in this sense, but F forces are in the opposite sense. You see the damper's internal force is proportionate with the velocity. The velocity which develops in the damper, the displacement which develops in the column. So the distance in the deformed geometry of the columns top and bottom ends is U much. This should be K divided by 2, K divided by 2. It's wrong. It's correct. So on the equation, this is the total acceleration acting to the mass. These are F's. F equals ma, an acceleration. Total F is so much. And then we obtain this equation here. Here you see, actually, there is a minus here. There is a minus here. This means that actually when the what's happening? Cause of ground. Because of ground motion, the structure changes its place, so the F force has negative sign. Means that afterwards, this ground motion creates an F motion, and your structure actually has this shape. The explanation of the negative sign here has this meaning. Let me explain this in another ways. This is a bus. A person is standing on it. As in the case of earthquake, the bus moves. So the legs of the person comes here. And because of that, a force acts to the person. And this force pushes the person to the backwards. Attached legs are still attached, but the person is pushed back. After the car or bus moves with an acceleration, you feel this, the physical effect of this action. You feel that one force is acting to you. Your legs are still on the ground, but as if you are pushed back. And because of this need, you search for somewhere to hold yourself in position, not to fall on the ground. The explanation is this, physical explanation of the mathematical formula. This sign. Now here in this expression, if every term in the equation is divided by m, I will get this equation. This is damping ratio. This is natural frequency, natural angular frequency. As understood from this equation, this u, actually it is ut because it depends on time, is a function of t, ground acceleration, natural vibration period or free vibration period, and damping ratio. Okay. So if two structures having same Tn damping ratio and UGT, they will make same structural displacement UT. For example, consider that we have one huge structure, one small structure. One huge structure has larger dimensioned column cross sections, beam cross sections, and it has a greater lateral stiffness shown with capital K, and this has a smaller lateral stiffness. And the mass of this structure is big M, this is small m. Since from the natural frequency analysis, the Tn of this structure is same as dn. And similarly, omega n and omega n, both structures are same. Since the ratio is same, assume that these two ratios are same. So these two are same and Tn are same. And assume that they both have same damping ratio, 2%. And they are subjected to the same earthquake. They are adjacent to each other. And the acceleration, ground acceleration, because of the same earthquake, is same. Their floor displacements in any time will also be same. For example, at time 2 seconds, this is equal to 3 millimeter, so this will be equal to 3 millimeter. From this property, which we illustrated using a single degree of freedom system, response spectrum graphics are created, which provides maximum floor displacement, but not the total displacement. This one is provided. And actually, this U and this U are same. But U 0 means the maximum. I don't know. From the book I have taken these books, this index number is used. I kept the same index. So this U and this U is same. But for a specific earthquake. For example, for El Centro earthquake, people during El Centro earthquake construct a lot of 1 degree, single degree constructions like that, okay, which has damping ratio 2%, okay, and theirs Tn's or omega n's are different. They all are subjected to the same ground acceleration as central. A lot of structures with same damping ratio and same natural vibration period or omega n. Okay. Then for different natural vibration periods, every structure makes different flow displacements and flow velocities and flow accelerations. So these graphs are obtained by measuring by means of some devices. Okay. This response spectrum is given to obtain the maximum flow displacement occurred during epicenter earthquake, maximum flow velocity occurred during epicenter earthquake, maximum flow acceleration, only acceleration obtained by derivating this one. Okay, but the maximum, not at an arbitrary time. During the whole acceleration, all flow displacements are measured, or from the measured values it's calculated, and we obtain only the maximum value, maximum flow displacement, maximum flow velocity, and maximum flow acceleration. Yeah. So response spectra is this. Okay. Sometimes instead of giving three response spectrums, one for maximum flow displacement, one for maximum flow velocity, one for maximum flow acceleration, these three spectra are combined with each other, and a combined spectrum of epicenter earthquake for 2% damping is provided in the literature. It's easy also to use. For example, here, if a single degree freedom structure is subject which has a 2% damping ratio, means 2 divided by 100, and has a natural vibration period of 2 seconds. 2 seconds. Here I come from 2 seconds. I draw a perpendicular line from here and reach to the curve. Okay. And this scale gives me the maximum velocity. I draw a perpendicular to this scale to obtain the maximum flow velocity. It's 23.5 inch per second. And I draw another perpendicular to this scale to obtain the maximum flow acceleration. It's 0.191 g, means times 9.81 meter per second square. So the maximum flow acceleration is 1.87 meter per second square. Okay? Okay, G means that. Multiply it with G. So G's unit is the unit of acceleration, meter per second. Or in English units, it might be inch per second square or feet per second square. If you draw a rectangle perpendicular from this point of curve to this scale, you will obtain the maximum flow displacement. It's 7.47 inch. Easy to read this information, as it is easy to read this information from those two curves. Now they are given here. And also, you can read just one of these flow displacement, velocity, or acceleration from the curve. Okay, it's enough that you have a state of combined response spectrum or three separate response spectrum. For example, you have just one response spectrum for maximum flow displacement. The relationship maximum flow displacement, the velocity of maximum flow velocity V or U0 dot is equals to angular frequency times maximum flow displacement. Forget this part here. Just they are same things. The same equation written here with different symbols. Here U0 and D is same and maximum floor displacement. U0 dot is the velocity, maximum floor velocity. UC, the ratio between maximum floor velocity and maximum floor displacement is omega n. Similarly, the ratio between maximum floor velocity and acceleration is again omega n. So the ratio between maximum floor acceleration and displacement is the square of omega n. Now here, omega n is calculated. Tn for Tn is 2. Here, these values are obtained for Tn is 2, where damping ratio equals 2%. This much. So we know the maximum floor displacement is this much. So if I multiply this with omega n, I will obtain the maximum floor velocity. And if I multiply the maximum floor velocity with again omega n, I will obtain maximum floor acceleration. Or if I multiply the maximum floor displacement, this value with omega n square, I will obtain maximum floor acceleration. Okay, you see? Here. Gravitational acceleration is 9.81 meter per square second, or second square. In terms of metric units, in terms of American units, it's 32.174 feet per second square, or 386 inch per second square. Here we have an easy numerical example. We have a weightless column. The lump mass on it is 52,000 pounds. The diameter and height of column is, diameter of the column is 4 inch. This diameter, it's a circular cross section has the column. I don't speak from this mass, from the column. Its diameter is 4 inch and its height is 12 inch. The damping ratio of this single degree freedom structure is 2%. Okay. The external diameter is 4.5 inch. Moment of inertia is so much. Moment of inertia of the column. Elasticity modulus of the column is so much. Calculate the maximum floor displacement, or top displacement, and the maximum moment and bending stress developed in the column. If the structure is subjected to eccentric earthquake, external diameter 4.5, diameter 4 inch. Yes. Actually, external diameter is important here. Now, this is the column and its cross section. Its pipe section. The external diameter is 4.5 inch. So the 4-inch is actually not required, as I understood from the solution of the problem, numerical example, because the moment of inertia of the column section is given, elasticity modulus of the material from which the column is made is also given. Now, this structure is, this is velocity, it's raised from there. Its unit is inch per second. The lateral rigidity of the column is the lateral rigidity or stiffness of the structure. Since the top of the column is free to move, it makes side sway. Its lateral stiffness of one column, the bottom of which is fixed and the top of which is free to side sway, is given by this equation. So 29,000 kilopound per square inch is its elasticity modulus. Moment of inertia is 7.23 inch to the power of 4. Yes, this is the unit. Divided by 12 feet equals to 12 times 12 inch cube of the column height. So we get the column stiffness, lateral stiffness. So and the mass, the weight is 52,000, so we shall divide it by ground acceleration to obtain the mass from the weight. Okay, we do it so. This makes 5.2 kilopound. We obtain the mass. These are the units. From this equation, we have now the stiffness and the mass value of the structure. Stiffness is obtained from the column. Mass is obtained from the lump mass. And we obtain omega and so. And from this formula, we obtain the Tn value of the single degree freedom structure. So here, from 1.59 seconds, which is the natural vibration period of our structure, we will obtain maximum floor displacement, velocity, and acceleration values. Now here, from here, we draw a perpendicular to the curve, find a point. Then from this point, we draw a perpendicular to the velocity axis. We obtain the velocity. It is 20. We draw a perpendicular to this maximum displacement axis, and we obtain the value 5. And then we draw a perpendicular to the acceleration axis, and we obtain the value 0.2 g. Okay, we got those values. Now calculate the damping ratio from this formula. Actually, we have the damping ratio. It's 2%. We have to calculate the damper's damping coefficient. The damping coefficient, we know the K, lateral stiffness, mass, and damping ratio is calculated here. These are its units. And then the internal force developed in the column is elastic forces plus damping forces. Okay, it's obtained conservatively for lateral stiffness times maximum displacement occurred at the top of the column at a time. And the maximum velocity, they might occur maybe at different times, but they are conservatively summed up so. Okay, and we obtained the internal forces developed in the column, which includes elastic forces and damping forces. Okay, so the total earthquake force, if we, instead of ground movement, if we assume an equivalent force act as a lateral earth force to the structure is so much, according to the shear force of equilibrium, it shall be equal to the internal force created in the column. So if you calculate the moment, maximum moment developed at the base of the column, we multiply this value with the moment arm, which is the height of the column. Yes, as you see here. We obtain this value in terms of kilopound feet, and if we multiply this value with 12, we will obtain this value in terms of kilopound inch. And from the simple bending normal stress formula, we obtain this. Moment of inertia is given in the question. Maximum moment is developed, is calculated here. R is the distance from the neutral axis to the most outside fiber in the cross section. So if this is the neutral axis, the distance from neutral axis to the outmost fiber is 4.5 inch divided by 2, which is the diameter radius, So we put this value, replace this value also in the formula, and we obtain the maximum bending stress. Okay, this is the solution. Okay, now the response spectrum and how to use the response spectrum is explained. Now I will explain the elastic design spectrum. Very brief explanation, it's very easy to understand. As it is well known, not only El Centro, but many earthquakes occurred and still occurs in our world. Therefore, the structural analysis cannot be done by trusting and using only one earthquake response spectrum. Thus, another response spectrum, which is the average of all response spectra occurred in one place, is created. However, in this situation, the structural analysis is done for an earthquake, which can be exceeded with 50% probability. Now, let me explain. So, let me finish the reading of this text. If another response spectrum is created, so-called another spectrum, using the maximum values of all the response spectra, the structure which will be designed using it will be very expensive. Therefore, using all spectra, the so-called another response spectrum is created, which will not be exceeded with 84.1% probability. This so-called another response spectrum is referred to as elastic design spectrum. Here we see an elastic design spectrum. Now, let me exemplify this. Not a combined response spectrum. Doesn't matter. For example, this is displacement, and this is Tn. And my response spectrum is something like this. It's a curve. But instead of this curve, I want to use an idealized response spectrum, which is created by straight lines, which is approximated by straight lines. Okay, this is the first thing what we do. Okay, this is our response spectrum. For example, as think that we are in Chicago, and I created a response spectrum, and El Centro happened in Chicago, and because of El Centro earthquake, from the devices measured the earthquakes, and after some further calculations are done, I obtain this response spectrum of maximum floor displacement. And then Many other earthquakes developed at Chicago, at the same place. And the response spectra from other earthquakes are those. Okay. Now, if I think that this is the higher one, or let me draw something like this is the third response spectrum. For example, to be 100% sure that the maximum floor displacement will not be exceeded by earthquakes developed or happened, or anyway happened in Chicago, not because of El Centro or because of two other earthquakes, I prefer to use this response spectrum. But the values are here too much, okay, in comparison to the values you see here. That's why this is a very expensive solution. Better don't use a response spectrum like that. It is told to us. If I take the average values, I will draw something like this. Okay? But this is not safe if you think this response spectrum, this response spectrum. This is also not convenient. And then they say this was the response spectral envelope, which is created thinking the maximum values of response spectra. Use the value of the maximum and multiply the maximum value with 0.841 and draw something like this. Okay. This is called elastic design spectrum. Not very expensive. This is elastic design spectrum, which is created from the response spectrums of the earthquakes developed at the same place. Not 100% safe, but 84.1% probability it is safe. But there is approximately 16% risk margin. Okay? That's elastic design spectrum. Now, this curve is belong to one response spectrum, which belongs to El Centro. We idealize this response spectrum using straight lines. And there are other response spectrums of the earthquakes developed at the same place. We combine them so that the maximum values of floor displacements, floor accelerations, and floor velocities will not be exceeded with 84.1% probability. And depending upon this mathematical approach, we create, using this response spectrum and many other response spectra, we create one spectrum. And we use only this spectrum to make our structural dynamics calculations in Chicago, and determine the earthquake forces which may act upon our structure. And it is called elastic design spectrum. It is used for elastic design of our structures. That is elastic design spectrum. Thank you very much. I will put this document to my website. Please subscribe to my channel. I am waiting your support. I also want to